Let's look at a couple more examples of using Stokes' theorem. So here let's find the circulation of this vector field here around this circle x squared plus y squared equals 15 in the plane z equals 5. So right, we're up here in the plane z equals 5. This is 5 units above the xy plane. And there's this circle whose radius is apparently the square root of 15, which is a kind of an awkward number. So we could parameterize this directly, but I mean, you know, having this e of x to the y, this makes me nervous, because when we parameterize this circle, going clockwise from above, when we parameterize this circle, we're going to get sines and cosines popping out, times exponentials. I mean, it seems bad, right? It seems really, really bad. So let's see if Stokes' theorem gives us a better option. I guess let's start by thinking about what sort of surface we could choose. Now, one thing that isn't obvious about Stokes' theorem is that if all you have is a closed curve that bounds a surface, you can actually choose any surface you want to evaluate the integral, right? So we could use a surface that goes up like this and has this circle as its bottom rim. We could choose a paraboloid that goes down like this and has this circle as its top rim. There are lots of choices. So of course you want to make the easiest choice you can, and I think it's pretty clear that since this circle is in this plane, we could, for the surface that this curve bounds, we could just use this disk in the plane. So that's going to be the easiest thing to do. So for our surface, let's use the disk where x squared plus y squared is less than or equal to 15 and z is equal to 5. Okay, now what is the compatible orientation? So if we're going clockwise around this disk, right, using the right hand rule to keep our middle finger pointed into the circle and our index finger pointed that way, we need our thumb to go down, I think. Yeah, we have to have our thumb going down, so we have to orient this downwards. Oriented downwards. Okay. Another nice thing about this, choosing this disk, is that because this disk is confined to a plane that's parallel to the xy plane, d sigma is just dx times dy. Right? This is sitting over the xy plane, and if we have a point, let me clean this up a little bit. If we have a point down in the xy plane, if we're using x and y as our parameters, and we have a point down in the xy plane corresponding to a point up on the surface, the little patch of area down in the xy plane is going to be the same size as the little patch of area near that point up in the disk at z equals 5, because these two planes are parallel. Right, so d sigma is just going to be dx dy. So that's especially nice. So this is starting to look good. Let's figure out what curl of this vector field is. As long as the curl doesn't turn out too messy, I'd say the surface integral is going to be the way to go on this one instead of the line integral. So let's see, we need partial derivative of p with respect to z. That's 0. That's nice. That knocks out all of the exponential stuff. Minus the derivative of n with respect to z, which is going to be 2x, and then derivative of m with respect to z, which is y, minus the derivative of p with respect to x, which is y e to the xy. Okay, that's unfortunate. And then for our last coordinate, derivative of n with respect to x, which is 2z, minus the derivative of m with respect to y, which is z. Okay, and I think I made a mistake. So derivative of, this should be the derivative of p with respect to y. So that's not 0. That's x e to the xy. So things are looking maybe not great at first, right? X e to the xy minus 2x comma y minus y e to the xy comma z. But the normal that we can choose, right, so we already know d sigma is dx dy, so if we want to do a surface integral, we also need to pick a normal. We know it needs to point down. We know it needs to be unit length. Well, that's 0, 0, minus 1, right? We don't need to do any calculation to figure that out. We can just write it down. And when we do the dot product of the curl with our normal, that all of the messy parts of the curl will all disappear. So this is looking really nice. Also, z for this surface, z is 5. So when we switch to the line integral over the surface of curl f dot n d sigma, right? Normally we would do a bunch of work to parameterize these things, but in this case, this is just the integral over this disk of, let's see, curl, right, we're doing the curl dotted with n, that's just minus z, and then d sigma we noticed was dx dy, oh, and z is 5. So this is just going to be minus 5 times the integral over the disk of dx dy, but that's just going to be, right, this is just the area of the disk. And the disk has radius square root of 15, so this is minus 5 times pi times r squared, so pi times 15 squared. So whatever this turns out to be, minus 75 pi, something like that. All right. So this one turned out pretty nice because when we chose an appropriate surface, the normal vector turned out to be very simple, right? And that made this much nicer. Okay. Let's look at one more example. So let's look at the circulation integral around this curve where c is the intersection of this plane, x plus y equals plus z equals 1, and this cylinder, x squared plus y squared equals 9, oriented counterclockwise from above, and then we have a vector field. So this plane, it's some angled plane sitting in 3 space, and then there's a cylinder, right? And this cylinder is going to intersect this plane in some angled circle like this, which I guess is another name for an ellipse. So an ellipse like this, and we're going counterclockwise from above, so that's going this way. All right, and let's see. So this surface, or again, as in the last example, because this curve is closed and it bounds a surface, it bounds lots of different surfaces, and we get to choose the nicest surface we want. And definitely we want to choose, if we can choose something that is a planar surface, that would be a good idea. So let's use this it's not quite a disk, elliptical disk, I guess you would say, that is in this plane. So to do that, let's find the curl of f. So it's going to be 0 minus 0, and then x squared minus 0, and then y squared minus 0. Okay, so there's our curl, 0, x squared, y squared. Now we need to parameterize this surface. So we can use the graph parameterization, I guess. So we can write this as z equals 1 minus x minus y. And then our parameterization is just x, y, 1 minus x minus y. As usual, for the graph parameterization, Derivative with respect to x is 1, 0 something, and that's going to be minus 1 in this case. Derivative with respect to y is going to be 0, 1 something, and this partial derivative is minus 1 again. And then the cross product is going to be, so 1, 1, 1. Okay. Notice that when we used the graph parametrization, we actually got the normal vector that is sitting in the equation for the plane here. That's not a coincidence. That actually always happens if you use the graph parametrization to parameterize a plane. At any rate, so now that we have the curl and we have our normal vector, oh, also notice that this is oriented upwards, which is what we need. Right, going counterclockwise around this, we need the upwards pointing normal, which is what we got. So we don't need to stick an extra minus sign on things. So switching to the integral, now we used x and y as our parameter, and so we're integrating over this disk in the xy plane, and this disk has radius 3. Right, so we're integrating over x squared plus y squared less than or equal to 3. I'm sorry, less than or equal to 9. Okay, and we're taking the dot product of our curl, which is 0 x squared y squared, dotting that with 1, 1, 1, and dx dy. Okay. All right. So this is the integral over this disk of x squared plus y squared dx dy. All right, now we have to evaluate this integral, but describing the bounds in terms of x and y coordinates is kind of clumsy. But now that we have this integral, we can treat this double integral as if it's a regular old double integral, and if we want to switch to different coordinates, we can. Let's switch to polar coordinates, right? So if we switch to polar coordinates, right, we're integrating over a disk of radius 3, so theta is going to go from 0 to 2 pi, r is going to go from 0 to 3, right, our area element dx dy is r d theta, and then x squared plus y squared, that's r squared. So what we're integrating is, let's see, our theta integral we can separate. It's integral from 0 to 2 pi of d theta, and then our r integral is from 0 to 3 of r cubed dr. So the theta integral spits out at 2 pi, and then the r integral spits out 1 over 4 r to the 4th from 0 to 3. So that's going to be, let's see, 2, and we can simplify a factor of 2 here. So pi over 2 times 3 to the 4th, which is like 81, right? So 81 pi over 2. All right. This r here, so one thing that can cause some confusion is when do you stick this r here, and when do you let the machinery of vector calculus, how we parameterize these integrals, when do you let that machinery spit out the appropriate volume element? So when you stick an r here is when you have a double integral, right? Forget where the double integral came from. If you have a double integral written in terms of x and y, and you are switching that double integral to polar coordinates, that's when you stick the r in here, sort of manually, so to speak, right? If we had, at the very beginning, right, we used the graph parametrization. If we had used a different parametrization, if we had used the parametrization, say a parametrization inspired by polar coordinates from the very beginning, then maybe using r and theta as our parameters, x would have been r cosine theta, y would have been r sine theta, and then z would still have to be 1 minus x minus y, so 1 minus r cosine theta minus r sine theta. If we had worked out our parametrization, right, this cross product to parameterize our surface integral, this would spit out the appropriate factor of radius, right? It would make this factor of radius show up on its own, so to speak. Well, that in combination with writing the curl in terms of r and theta, right? So if you parameterize with polar coordinates from the very beginning, you don't need to stick anything else in manually. The machinery of vector calculus will take care of it. If you write and rewrite a surface integral as a double integral using Cartesian coordinates, and then you take that double integral and switch to polar coordinates, well, now you're just doing a regular coordinate change in a double integral. That's when you have to stick this r in here.